Yes, then we are going to examine the stability of nonlinear system. This is lecture 5, and the problem in hand is determine the stability of the following system with on-off controller. The on-off controller is this one, and the plant function is this one, and we have to determine the stability of this system. So as discussed during lecture 4, we need polar plot of this plant function, and also plot of minus 1 by nx as x varies from 0 to infinity. So first, in fact, let's talk about polar plot. So GS plant function is this one, and put S is equal to j omega gives us this one. Magnitude part is this one, phase part is this one, and we are going to show in the table that how m5 varies as omega varies. So for omega is equal to 0, we can see that m is 5 and phi is 0. For omega is equal to 1, m is approximately 3 and phi is minus 47 degree. And for omega is equal to infinity, m is 0 and phi is minus 270 degree. So the polar plot is like this, starting from here, passing through this one, and it lands the origin like this. Now coming to the describing function, we already know the describing function of this on-off controller. This is nx is equal to 4m by pi x 0 degree. M is here 1, so 4 by pi x, and so minus 1 by nx is minus pi x by 4, that is minus 3.14 by 4x. So in this table we are going to have the values of minus 1 by nx as x varies from 0 to infinity. So for x is equal to 0, this is minus 1 by nx is 0. For x is equal to 1, this is minus 0.785, and finally at x is equal to infinity, minus 1 by nx is minus infinity. So that has been plotted like this. Now it is very obvious that intersection of g omega and minus 1 by nx at a represents limit cycle. As an observer traverses g omega in the direction of omega, the portion OA, this portion lies to the right of the g omega curve, that is polar plot, and the portion AC, this portion lies to the left of the limit cycle, lies to the left of g omega. So that's this means that the limit cycle at A is stable, and in this region the system is going to be unstable, and in this region the system is going to be stable. Now to determine the frequency and amplitude of the limit cycle, we are going to put the condition that we are at point A. So at A, phi is equal to minus 180 degree. So from phase angle, this is minus 180 degree. So after solving, we are going to get the result as ki omega is equal to 10.95 radian per second, and this is frequency of limit cycle. The magnitude of limit cycle can be determined from magnitude of this polar plot. Okay, so 5 upon omega square plus 1 root under and 0.01 omega square plus 1 omega set to 10.95, and this has fastest result as 0.262 unit. So we mean to say that at A we are going to have limit cycle with amplitude 0.262 unit and frequency 10.95 radian per second, and in this region the system is going to be stable. In this region the system is going to be unstable. In this region the system is going to be stable, and at A we are going to have the stable limit cycle. I hope you must have understood the concept of the stability determination by describing function method. Thank you.